Thanks so much for the invitation, and thanks so much for joining. Three-part talk, and I hope at least one of the three parts interests you. So something for everyone. Here's the three graphics to keep in mind for the talk. So on the left is going to be our image for when we're talking about measurement reduction, and I'll explain what this is. In the middle will correspond to the generalized Clifford groups. So these you might recognize as the 5 platonic solids, and these pop up in an interesting way in quantum compilation related to an open problem that I'll tell you about. And the last one on the right, combining the two biggest buzzwords that we have right now, quantum computing and AI. So this is neural quantum phase estimation. Despite the fact that they're very big buzzwords, I'm actually quite optimistic about this approach. And I'll tell you about how I hope we can actually run some reasonably scaled, large-scale phase estimation experiments in the near future. So feel free to interrupt me at any point if you have questions. I'm happy to keep things, more of a dialogue than a monologue. So the first part will be on measurement reduction. And this, I should mention, by the way, the latter two ones are sort of work in progress, but I'll present our preliminary results and ideas there. This one is the more finished one. So there are papers that you can refer to here. Over the past few years, 2 or so years, we've done work in this area of measurement reduction, which I'll define formally, but basically you have a Hamiltonian, or generally some observable. Usually we'll think of this as a Hamiltonian, and you want to compute its energy on a quantum computer. And there's a very large laundry list of techniques to do this now. So we've written these 3 papers, and I'm going to talk mostly about the first one and the last one. The first one is in PRA as of last November. The last one is on arXiv as of last night. So you can now check this out, though. The other one, if there's questions about that, the non-Clifford diagonalization, I'm happy to mention that at the end, but I'll just focus on these 2. So what do I mean by this problem of energy estimation? So as I mentioned, we're going to be given some Hamiltonian, and I'm always going to write that in the Pauli basis. So sum over I going from 1 to, let's say we have capital N terms. Each Pauli, PI, will come with a coefficient CI. And Pauli, n-qubit Pauli, so this is an n-qubit Hamiltonian. Each PI is a tensor product of identity X, Y, or Z. So our goal is we want to compute the energy of this, and we want to do that on a quantum computer. So the energy estimator we're going to denote as E bar, and that's the expectation value of the Hamiltonian H. It's worthwhile saying, we have this notation, but it's important to note this is always with respect to a particular state, right? You have to compute the energy with respect to a particular state, and the state that you're in actually can have important effects on what the total number of measurements is, or equivalently what the variance of the estimate is. So always keep that in mind. Will usually be abstracts. It's the energy itself, but it's always with respect to a particular state. And just by linearity, we can of course write this as a sum over the individual expectation values of each Pauli. So that's like the no technique way of doing this. How would you do this on a quantum computer? You would run capital N experiments. In each experiment or each circuit that you run, you would measure one of these expectation values. Okay, that's not going to be very scalable for a variety of reasons, and so we would like techniques to do this faster. I'll mention a lot of techniques, but for now, I just want to focus on the total number of measurements. So the problem that we're given is, compute this energy. This is an unbiased estimator to within some accuracy epsilon. Okay. So the thing you care about really is the accuracy that you want. So that's going to be our epsilon. And then the thing that dictates that is the variance. That's what you want to try to minimize. So we can write this if we group the Pauli terms PI into commuting sets or groups, which I'll call them. Then we can define that sub-observable, if you will, OI. And the important thing is that the total number of measurements that you need, that's the M here, will scale by this thing that depends on the variance. Okay? So this little m, I'll explain, is the number of groups that you have. And we're going to focus on these grouping methods to try to squeeze as much information as we can out of the quantum computer in as few experiments as possible. Okay, so basic setup. And now, before I get into the grouping methods, here's part of the laundry list. There's a lot more than this. So maybe a lot of you have heard of classical shadows and all of the variants now. So there's a lot of flavors of this. Locally biased classical shadows. There's adaptive formulations, as well as many others that I'm not listing here. Some of the other techniques to do this go by the name of informationally complete POVMs. There's these grouping-based methods, which are the ones that I'm going to focus on. So grouping and overlapped grouping, I'll explain these in a lot of detail. But before we even get into that, just to mention the other ones, because it's important, machine learning based methods. So this would be given data about your quantum state. You want to do some tomographic procedure, do some tomography, try to learn a model of that state, and then you can output expectation values of new observables that you haven't seen before, that you haven't trained on. So that's a thing that people do as well. If you can also compute reduced density matrices, KRDMs, so K being the size of the reduced density matrix, the number of qubits that it acts on, then from that you can compute expectation values of observables. So that's another strategy to do this if you have some way of efficiently computing KRDMs. And then you can tailor it to particular systems as well. So if you know from the start that you have some fermionic Hamiltonian, then there's additional symmetries or properties of that Hamiltonian that you could exploit there. And people do this. For me and for us in these papers, we're going to keep it general. So just given some prescription in the Pauli basis, we don't know whether it's fermionic or bosonic or what it is. We just want to take the description that we have in the Pauli basis and try to compute the energy as efficiently as we can. So classical shadows techniques have received a lot of attention in recent years, and there is a lot of virtue to them. But if you have a problem where you already know what the Hamiltonian is, then it's usually almost always better to use information about that problem. And this table is, there's a lot of information in this table, but what I want you to take away from this is, here's a bunch of classical shadows methods that they're applying. So if we look down here, a diagonalized version, de-randomized, and then de-randomized. And in most of these cases, the de-randomized versions are going to be performing the best. Okay? So you can get a sense of actually how many measurements you need to do as a function of the size of these molecules. So here is a hydrogen molecule, which acts on 5 qubits, in this 321G basis that they've chosen, and all the way up to a 16 qubit molecule, nitrogen, in the STO6G basis. So the number of measurements, even for relatively small molecules like this, is usually on the order of like 10 to the 6, a million, or 10 to the 7, 10 million. Okay, and as we scale this up, this is going to also scale up. And so quickly, for molecules that are of interest, you get into the billions of shots, trillions of shots. That's experimentally challenging. Superconducting qubits can sample very fast. They have a high sampling rate. Other platforms, not so much. So this is actually can be a big bottleneck in quantum algorithms. And it's an important problem to have good techniques for. So shadows techniques, classical shadows, I like them a lot. They're best suited for when you actually don't have any information about what the observable is, and you just want some efficient description of the state in that sense. If you know some information about the state, usually always, I think it's becoming clear in the literature, and I'm certainly of the opinion, it's best to just use that problem information that you have in order to extract the most out of the quantum computer. Okay. So here's the segue into grouping-based methods. These have been around for a while and has this nice graphic visualization. So here's a, I believe, 2019 paper, which introduced a lot of these ideas. And what's going on here is we're going to represent our Hamiltonian as a graph. Every node in the Hamiltonian is a particular poly, and you can see them labeled here. And then we'll just put an edge between polys that commute. So this Z1, Z2, Z4 commutes with Z1, Z2, obviously. So there's an edge here. Whereas this Z1, Z2, Z4 does not commute with X3, X4. The issue is the Z and the X on qubit number 4, right? So those don't commute, so there's no edge between those two. Okay. In this setting, the problem of grouping boils down to a clique covering problem, which has been well studied in graph theory. There's a lot of good methods for this. And for a long time, for a few years at least, this was sort of the method that people were doing. And why do I want to do this? Well, instead of the absolute, most basic method of just take each poly, measure it on the quantum computer individually, if things commute, they share an eigenbasis, they can be measured simultaneously, right? So in this case, instead of how many terms do we have here, 6, if I did this grouping into 3 groups, then I would have, or 2 groups, sorry, 2 groups of 3 terms each, then I would have 2 circuits that I need to run on hardware, okay? And the covering problem, the clique covering problem is hard, it's NP hard. And so you might not find an optimal clique, but there's good heuristic algorithms to do this. And so you might find, for example, a covering which has 3 groups. That would not be as good as 2 groups. Okay, so these ideas have been around for a while. It was quickly realized that the number of groups is not the important parameter. Why is that? What is this ignoring? It's ignoring the key thing, which is the coefficients Ci that appear in this variance expression that I wrote down. So in this variance, imagine computing the variance of a poly, it's going to go by like the coefficient of the first one times the coefficient of the second one. Okay. So just the number of groups is not the key thing if you want to reduce the total variance, which is equivalent to reducing the total number of measurements that you need. Okay. And this was quickly realized that maybe it took a year or so. And there's a really nice paper which spells this out by Crawford et al. Efficient quantum measurement of Pauli operators in the presence of finite sampling error. What they do here is they introduce an algorithm that they call sorted insertion, which is very simple. It's just designed around this idea that we know that the larger coefficient terms are going to contribute to the variance form. So what they'll do, instead of just trying to find any clique covering, without regard to the coefficients, they'll first sort the terms by magnitude of the coefficient. So we'll have some A, B, C, D terms, etc. That the first A term is, I'm thinking of it as the coefficient times the poly, and the coefficient for that A term is going to be the largest in magnitude. Okay. So that's the sorted parts and sorted insertion. And then the insertion part is just going to be a grouping algorithm based on this ordering. So what we'll do at the start, it's very easy to just visualize this. We'll look at the first operator that we have, A, and we don't have any groups yet. So all we do is we just make a group A, and this is our first group, okay? Then we go to the next operator, B, and we check if A commutes with B. If A commutes with B, we put it in the same group. If it doesn't commute with B, then we have to form a new group. So let's suppose in this case that it does not commute, so we would have to form a new group. So we have 2 groups now, A and B, and then you just keep doing this for all of the terms. Unfortunately, commutivity is not it's not transitive. It's not an equivalence relation. So you do have to check not just one term in the group. You have to check all of them. So if we look at C, I would check, does it commute with A? And maybe it does. So I would have a group that looks like this, A and C, and then I would go on to D, and I would just keep doing this. And eventually you'll come to another grouping. You'll have some number of groups, but the first group will correspond to, you hope has the terms with the largest coefficients, and that dictates the variance. If those are all measured together, then you can reduce the variance in the estimate and reduce the total number of shots that you need. So that's the sorted insertion technique. And let's suppose in this case that we ended up with 3 groups, A, B, C, A, C, B, and then D. The other thing that you need to do after you figure out what the groups are, and this is true for any grouping method, is assign a number of samples for each group. So we'll imagine we have some fixed measurement budget, capital M. I would want to assign some number M1 of shots for the first group, plus some number M2 of shots for the second group, plus some number M3, such that it fits within my total measurement budget. So there's sort of these two steps for the grouping methods that are important to remember, so you understand what I'm talking about when I get to our papers. The first one is how to do the grouping itself. And then the second one is what we'll call the shot allocation, as how to allocate the shots between the groups in an optimal way. Usually you'll want this to be proportional to the sum of all the coefficients in the group. That's one strategy that is just intuitively makes sense. That's what's going to dictate the variance, and so you would want a number of measurements proportional to that. Okay. So this works well. That's the algorithm. Here's some results. So now here's comparing sorted insertion on the far right versus all these other grouping-based algorithms which did not take the coefficients into account. And the bold entry is the best one here. So R hat is a certain metric. The higher it is, the fewer measurements you need. So they're showing in this paper that the sorted insertion metric on almost all of these sort of small scale molecules between, well, H2 is very simple. It's just on 2 qubits. Sorry, this is the total number of terms in the Hamiltonian versus going all the way up to 120 terms. That's sorted insertion is usually. Okay. So a well-performing heuristic algorithm. The first paper I want to tell you about from our work is this paper, which we call, well, introduces a new definition of commuting that's very simple. It's called K-commuting. And that could be used in this procedure of grouping methods, whether it's sorted insertion or any other method. That gives you some benefits, allows you to do some trade-off. So to motivate this, I want to just point you to the term qubit-wise commuting. If any of you have read these papers, you'll have come across this term. This just means the following. So rather than checking if in the commutativity graph, if 2 strings commute fully, we'll check them on each individual qubit. So what do I mean by that? Let's suppose I have 2 poly terms. Let me use one of the examples that we have here. ZZI and CZII, these are 4 qubit terms, and XXYY. So these are 2 that come from the bottom graph here. And these don't commute. Sorry, these do commute. They do not qubit-wise commute, okay? So there's no edge between these terms in this graph, if you can see that, make it out. They also do not qubit-wise commute in the following sense. By qubit-wise commuting, we mean we look at each pair of terms. So I look at the first term, and this is the qubit-wise parts, per qubit, whether each poly commutes individually on every qubit. If that's the case, then we say that they qubit-wise commute. And if that's the case, then there's a efficient quantum circuit for diagonalizing this. It's just a depth 1 quantum circuit, because all you need to do is rotate each qubit into the corresponding eigenbasis. So the diagonalizing circuit for qubit-wise commuting terms is just a single qubit poly rotation at the end of the circuit. Whereas with full commuting, you might need some more complex basis diagonalization. Okay, and this idea got a lot of attention, but it always bothered me because I don't understand why we just restricted to single qubit commuting versus full commuting when there's obviously a spectrum that you can interpolate in the middle. So that's K commuting. So K is some parameter. K is a number between 1 and the number of qubits that you have. If K is 1, you recover qubit-wise commuting. If K is N, you recover full commuting. But you could also have these intermediate values. So this is the example that I wanted to highlight because these 2 terms do not qubit-wise commute, but what we would say, they 2 commute for K equals 2 because ZZ commutes with XX, and then identity on the other terms, these also commute. So you have these 2 blocks of 2 qubits, so these would commute for K equals 2. Why is that useful? Well, it's useful because it reduces the depth of the diagonalizing circuit. Okay? So you can think about forming this commutativity graph in this paper. That's what we're doing. We introduce this just very simple definition of commuting, which is across blocks. You can think about this in a tensor product basis. Whereas the smaller k is, the lower the diagonalization circuit depth will be. But potentially you'll have fewer terms that you can group together because there's less edges in this graph for qubit-wise computing in small k. But as you ramp this up, you can potentially squeeze more terms in at the cost of the diagonalization circuit depth increasing. Okay. So that's all we're doing in this paper. And it's a very simple thing. And just wanted to write a paper about this. But we actually found some interesting features about this with particular families of Hamiltonians. So basically what we found is that certain Hamiltonians will exhibit a value that we call k star. It's a number which scales potentially sublinearly in n, which is the largest block size that you need in order to sort of get the maximal measurement reduction. So here's an example illustrating that from the paper. We considered the Bacon-Shor Hamiltonian, which is a Hamiltonian that appears in several areas, often in quantum error correction. This is defined by having a square lattice of qubits, and on the horizontal edges, you put X operators, two-body operators. On the vertical edges, you put poly-Z operators. Okay. So from this Hamiltonian, you might expect intuitively from the locality of this and the way it's defined that something might like this might be true. And that's what we see. So this R hat is the same R hat from the sorted insertion paper. And basically this saturates for a value of which is less than the number of qubits in the Hamiltonian. So what we're varying here on the horizontal axis is the k and k commuting. And we know that when k is equal to n, which in this case for what we did is corresponds to the far right on the plot here, then we'll achieve the sort of maximal measurement reduction possible. But this notion of k commuting allows you to achieve that maximal reduction at potentially a smaller value. And it's not in all Hamiltonians, but there are a family of Hamiltonians which exhibit this asymptotic behavior. And that's what we're plotting in the bottom here. So this is this k star that I mentioned, this asymptotic value versus the number of qubits. And we show in the paper, we prove that this scales quadratically the square root of n. And obviously the numerics match this. So that was something interesting that popped out of k commuting, which was nice to see. Really, we were thinking about this more practically in terms of how can I minimize the number of measurements that I need and keep the circuit depth small so that it can actually be run on hardware. So it does work well in that case for general molecules. There's not always this cutoff value of k star, but it still seems to work well. So here's an example of that. So this is a chain of hydrogen atoms. There are n over 2 hydrogen atoms on a line for a total of n qubits. And we're plotting this, again, R hat metric. The higher this is, the better. The higher this is, the fewer total measurements that you need versus the k, the block size that you're using in k commuting. And what you see is this interesting behavior for different sizes of hydrogen chains from 32 qubits up to 64 qubits. That's, you can get a pretty large reduction. So this R hat of, say, this is around 200. This means that it's like 200 times better, 200 times fewer shots than no grouping method, okay? And you can do better of that if you consider the fully commuting case, which has been done before, but that's going to come at the price of a larger diagonalization circuit. So depending on your budget of how noisy the quantum computer is versus how many measurements, how many groups you can afford, this is a new definition of commutativity that allows you some flexibility. Okay. Yes.
So it seems like, generally speaking, those one at a time. Yes, a good large decay. Sometimes also.
Yes, great question. So the question is, why is it not monotonically increasing? And it's an interesting feature. Let's consider a 3-qubit example. Let's have XXZ and ZZX. These do not qubit-wise commute. They do 2 commutes. So if we consider the block size of 2, so you can put them together. Actually, in this case, they don't 2 commutes, so this is not a good example. What would be a good example of this? I can still tell you the intuition. The intuition is that you can have things which 2 commutes, but do not 3 commute, for example. And that's why it's not monotonically increasing. If they do 2 commutes, then for any constant value c times k, then you'll have that as well, and you can see that in the numerics. But it's not strictly monotonically increasing. Yeah. Someone can think of an example which satisfies this. It's hard to think and speak at the same time. Great. Other questions? So now I'll move on to the next topic. That was the first paper. This was the recent paper. So here's the idea of overlap grouping. So we're not the first to introduce this. This has been around at least since 2023, and it was actually hinted at in the first paper of sorted insertion that I mentioned. And what this means is, again, once you sleep on it for a day, it's obvious that you should be doing something like this. But the grouping methods from before, we were saying, if everything commutes, put it in this group, and then we're done. So that would be a non-overlapping grouping. We could have a group which looks like this, Z1 in one group, and then Z1, Z2, X1, X2 in the other group. But we also have that Z1 commutes with Z1 and Z2, right, obviously. And so, again, a very simple idea, just overlap grouping. Why not put this Z1, Z2 term in both groups? So that's pretty much the idea of this paper, this NPJ quantum information paper, and they introduced this and they explored this, and they sort of showed numerically, which I'm showing here in this table, that there are algorithms for doing this. ICS is an algorithm for doing this. Iterative coefficient splitting is producing the smallest variance of these other methods that they're considering. And I just want to highlight one other one. SI is the sorted insertion metric. Okay, so you can get a sense. Again, people study these on like these very small molecular benchmarks, which isn't my favorite thing. I think we could do better than this. But for hydrogen H2, every method is the same. It has two terms and it's Hamiltonian. But for like NH3, more interesting molecules, variance of 18, in some units of energy squared, that doesn't matter, versus a variance of like 3.3. So there's a non-trivial reduction that you're getting from doing these overlap grouping techniques. So these have been introduced. They've been studied numerically in these previous papers that have come out in the last 2-3 years, but they haven't really been very well understood, and that's what we wanted to do. So we wanted to ask the very simple question, okay, numerically it seems to be working well. What is the maximal variance reduction that you can hope to get by doing this overlap grouping technique? So very simple question, and we did come to a satisfying answer to it. And that's what this image is illustrating here. So the answer is that the maximal variance reduction you can get will scale with the number of groups that you have in the original disjoint grouping, so the non-overlapping grouping. Okay. Now, already you have to ask yourself, okay, maximal variance reduction relative to what? What are we comparing it to? It's easy to just pick some very bad grouping technique, and then you can sort of artificially inflate the variance reduction. We didn't want to do that, so we're comparing it to the sorted insertion heuristic, which has been proven to work well for these disjoint grouping technique on a variety of molecules. So the statement essentially is that relative to sorted insertion, the algorithm which produces a disjoint grouping of little m groups, you can at best achieve a variance reduction that is proportional to this number of groups. Okay, and if you further assume something about how you're allocating shots and assume a zero covariance, which is something that people do. Sometimes it's more appropriate than others, but in this case, if you assume zero covariance, this is actually the maximum variance reduction that you get. Okay. And here's the image that I showed at the start for how this goes, the sort of illustration of the proof. And let me just sketch, a little bit behind on time, let me just sketch the idea of the proof. So basically what we do is we construct some commutativity graph, right? We can define the Hamiltonian in this way, as I mentioned, such that sorted insertion will obtain a disjoint grouping that looks like what you see on the left here. So just to describe this graph, again, this is, it would be strange to find a Hamiltonian which looks like this, but we don't care. I just want to know what is the best possible variance reduction that we can hope to get. And so we're explicitly constructing the graph which achieves that. This consists of some number, called it n, of complete graphs. So there's n, k, n graphs. In this case, it's n is equal to 5. In addition to being a complete graph, they're connected to every other complete graph on the interior. So those are all the edges that you see in the middle here. And then we have n minus 1, what we call exterior nodes. Those are the nodes that you see, well, on the exterior here. There's one for each complete graph, except for one that's missing here. And just to give you the sketch, the way this goes is that, once you run sorted insertion on this, the algorithm, if you assume the coefficients all have some equal weight, but enforce a small perturbation so that the ordering actually happens, then you obtain a grouping that looks like what you see here. So these different colors are the different disjoint groups that sorted insertion obtains. There's another valid grouping for this, which looks like the right here. Again, I mentioned that every node in the complete graphs in the interior commute with each other. So this is another valid disjoint grouping, and you put all the exterior nodes on the edge. Two valid disjoint groupings, and then from these, there's a partial order structure that this overlap grouping method induces. And you can actually sort of do the combination of these with the overlap grouping in the sort of best case designed for overlap grouping. So that is all the interior nodes are still together, but you also share the grouping of the each complete graph with this exterior node. Okay. And in this case, we're able to, for this constructed Hamiltonian, achieve this variance reduction of theta of n proportional to the number of disjoint groups. Okay. So why is that the maximal variance reduction that you can achieve? Well, you can just write down what the variance for the energy estimator is. When you do this disjoint grouping, overlap grouping, also known as coefficient splitting, there's a lot of flexibility that arises, and the coefficients W here are how much weight you're putting on each polyterm per group that it's in. So the flexibility arises because you'll still get an unbiased estimator as long as those add up to 1, but you can assign different weights to them. So we have this parameter W that appears here, and in the assumption of zero covariance, this is the expression for the total variance, this first term that I've written down. With covariance, you'll have covariances between all the terms that are in the same group as each other. Okay. But in this model of zero covariance, you can see that this expression for the variance will be upper bounded. This is just the intuition. It's, there's m terms here. We can single out the worst one that gives us the highest variance. So it'll be m times that. And this is why the variance, the maximal variance reduction is proportional to this number of disjoint groups. Okay. So we've sort of explicitly constructed this Hamiltonian. The last two equations on the slide, I'll just mention briefly, are how to actually allocate the shots between the groups. So I mentioned there's these two steps. One is doing the grouping, whether it's disjoint or overlap. And then the second step is actually assigning the shots per group. And this does have an effect on the variance. The sort of best way to do that here, like I mentioned, is to allocate it proportional to the sum of the total squared coefficients in that group. Okay. Again, there's a lot of flexibility here, and but under these assumptions, this is where you obtain that linear reduction in variance, which is the maximum one that you can achieve. Okay, so that is the first result that we proved. The second one that I'll mention briefly is how to actually do this overlap grouping. We introduced two algorithms for this. It's interesting that there is a setting in which you can do this after the fact. We call that the post hoc repacking, whereas this is the ad hoc repacking. You can do it after the fact, meaning after you've already collected all the samples from, say, a quantum computer per group, by only grouping terms which commute in that same basis. This ad hoc repacking is a little bit more general. It allows you to change the basis as you're regrouping the terms. So that's the gist of it. I'll just mention what we show about this algorithm is that it does, under mild conditions, but we have to assume something. Under mild conditions, like again, covariance being 0 and at least one refinement step, which is just think about it as one iteration of this algorithm, it adds at least one term with non-zero variance. Then in this case, this algorithm will actually always deterministically reduce the variance of the original disjoint grouping. And I'll just mention, I don't have it on the slides, but if you relax these conditions, that the covariance is 0, then you can get intuitively, it's easy to show that you have a non-increasing guarantee. So the overlap grouping will never be worse than the original disjoint grouping. So hopefully that's intuitive, as overlap grouping is just a special case of disjoint grouping. But under these mild conditions, which are true, usually for problems that we care about, then we have a deterministic procedure to reduce the variance. And to justify why that's usually true, we considered the similar molecular Hamiltonian benchmarks. So these molecules that we've seen, like NH3, CH4, et cetera. But we've also scaled it up to larger molecules that have been considered. So OWP is standing for a one water phosphates. This is a metaphosphates. In other words, we were thinking about ATP hydrolysis, and this is sort of a surrogate molecule which has similar features of that mechanism. And so, here's some numerics. We've proven the best case that we can hope to get. Here for each molecule, in parentheses, we're listing the number of disjoint groups. So this would be like, just think of it as that M, it's the maximal variance reduction that you can hope to get. In practice, we're seeing much less than that, but it's still a non-trivial reduction. So for this metaphosphate Hamiltonian, which acts on 44 qubits and has just over 500,000 poly terms, you can group them into around 2,700 disjoint sets. And then once you do this repacking procedure, that is there's different variations of this. In the best case, we get something like a 2.3, 2.4 reduction of the variance. Okay. So this is comparable to the previous numerical studies that I mentioned, which have done this. And it's not really getting too close to our sort of theoretical bound of how well this can perform. But you're still getting some reduction in the variance. Here, I'll just mention for completeness, again, what your state is important. So here on the left is an approximate ground states. Here on the right is the Hartree-Fock state, actually. So in both of these cases, we're pretty similar, but variance and energy, of course, depend on the state that you're in. We've also studied it for a different benchmark of random Hamiltonians. And in this one, we pick an n-qubit Hamiltonian, and we take a fraction of the total number of polys that you can have. So it's something like 2 to the n, and we'll take some constant fraction of that, call that alpha, as the number of terms in our Hamiltonian. And similar plot from before, you can see the number of disjoint groups in parentheses. And for this model, you do see something which goes like the problem size, meaning the variance reduction that you see generally increases for the larger problem that you have. And that's kind of true in the molecular benchmarks as well, but it's not as clean, and it can vary, depending on the molecule itself. But in this model, this sort of illustrates the behavior that we expect to see, which is this sort of linear reduction. And that's one reason why I'm actually optimistic about these overlap grouping methods. As we go to larger and larger quantum computers and we can solve larger and larger problems, the reduction that we're seeing here is generally increasing with the size of the problem. So it's already useful. It has been demonstrated in these previous papers. And as we get to larger and larger problems, I think it will be more and more useful. Okay, I'm significantly going significantly slower than I anticipated. So the middle idea is on generalized Clifford groups. Why don't I save this? If someone has a question, you can ask me at the end, or we can chat after. And I'll just fast forward onto to the third part, which is neural quantum phase estimation. This one is, again, the model of quantum plus AI. By the way, if you zoned out for the first part on measurement reduction, now is a good time to zone back in if you're interested. You will not have missed anything because we're switching gears. So neural quantum phase estimation. Let me go to some textbook just so we're on the same page. Quantum phase estimation algorithm. So it's estimating a phase, which is really to say it's estimating an eigenvalue. So I want to solve this eigenvalue problem. Given an n-qubit unitary U, I want to figure out what its eigenvalue lambda is. And because it's a unitary matrix, its eigenvalues all have modulus 1. And so they can be written as e to the 2 pi I phi for some number phi between 0 and 1 that we call the phase. We significantly overuse the term phase in quantum and physics in general, but here's the phase phi that we're estimating. The reason we're doing that is to solve this eigenvalue problem. So in the case that phi can be represented exactly with m qubits, then here's the quantum circuit which runs phase estimation to do that. You need an m qubit register at the top and the n qubit system register. So that's dictated by the size of the unitary U. And you prepare the equal superposition state. You do the sequence of controlled unitaries of successive powers. So first U, then U squared, all the way up to U to the 2 to the m minus 1. And then by an inverse quantum Fourier transform, you can show that when you measure, this outputs the bits in the binary decimal expansion of the phase phi, which I've written down here, exactly. So in a single quantum circuit, you can output the phase, which of course 1-to-1 corresponds to the eigenvalue. Okay, so in principle, this does not scale. This scales efficiently in the size of the problem, because on the qubit register here, n qubits, the number of times I need to do these controlled operations does not depend on n. That's sort of a hyperparameter. It's the amount of accuracy that I want in the eigenvalue estimate. Again, textbook algorithm, but it's worth mentioning. In the case that phi can't be represented exactly with m bits, you can still get an approximation of it. So you pick some number m, which given some accuracy epsilon that you want, again, does not scale with the size of the problem. So the algorithm scales efficiently, but the overhead is like insane. Imagine you ask an experimentalist to do a controlled U to the 2 to the m minus 1. They're going to leave the room. So this is a very challenging quantum algorithm to experimentally implement, but it's one that we like because it sort of has these guaranteed convergence properties and things like this. So there's been improvements to phase estimation, and I'll just highlight this briefly so I can get to the punchline of the work that we're doing. So the first thing is that you don't need to do all of these controlled operations in the same circuit. You can do what is called the iterative version of phase estimation, iterative QPE, where you learn like the last bits, and then once you learn the last bits, then you can learn the second to last bits, and you can keep doing this until you learn all of the bits. The advantage of this is that at any point, I only need to do one controlled U operation instead of like m of them. Okay, so that solves one problem, a qubit problem, dictating the overhead. but we still have these sort of long time evolutions, or many sequences of the controlled U that we need to apply. And so that's still challenging. So there's been other improvements for this. Time series quantum phase estimation. It appears in several papers, but I really like this 2019 paper by Rolando Soma, where the goal now, so we've sort of compressed the circuit vertically in space, that we'd like to compress it in time as well. The way to do that is, instead of actually doing the Fourier transform explicitly on the quantum computer, or having to do the exact sequence of controlled U to 2 to the 0, 2 to the 1, all the way up to 2 to the n-1 operations, you can do some other times that are potentially a lot smaller than the prescription that phase estimation gives. And so what he shows in this paper is, he gives the recipe for doing this and shows that it works. What you do in this case is that instead of successive powers of the unitary, we'll just do the unitary evolution. Again, here I'm thinking U as being equal to e to the minus IHT. And so we'll do that for various times. And smaller times than would appear in the original prescription of phase estimation. After you do that, you sample this function at these times, and then you just compute a Fourier transform. Here, we move the Fourier transform from the quantum computer to the classical computer. So with this discrete Fourier transform DFT, we can retain the spectral information that we want to get from this time series that we use the quantum computer as sort of a oracle to generate. Okay. So that was another big improvement of phase estimation. And then recently, in the last 2 years, October of 2024, there was another improvement of phase estimation that caught a lot of people's attention and caught my attention. Just from the title, quantum phase estimation without controlled unitaries. So, this approach is great. We've reduced the circuit depth, but again, still, if you ask an experimentalist to do a controlled time evolution, they're still going to leave the room. So we really need to solve that problem. And they've presented a sort of general framework to do that. What we do is, instead of doing the controlled time evolution like we had before, we'll do an uncontrolled time evolution where I prepare some initial state, psi, that's close to the eigenstate that we want. We'll evolve for some time e to the minus IHT, and then we'll unprepare that. And so that is to say, what we're measuring is this quantity that you see in parentheses here, this overlap, which is the previous signal that I've written down, but it's modulus squared. Okay, so with the controlled version of phase estimation, you get f of t, which is in general a complex value phase. In this case, you get the modulus of f of t, or it's square, it doesn't matter, which is real value. In order to do the discrete Fourier transform, you do need that phase information. Here, phase meaning the fact that it's a complex number. And so it's been known that you can do this version of the circuit for a while, but what they introduced to the quantum computing community is that people in signal processing have studied this problem for a long time, and they call this phase retrieval. So it's the problem of, given some real valued signal, retrieve its phase in its complex valued signal. So they sort of note this, and they apply sort of 2 modified textbook phase retrieval algorithms for this, which I list down here. And I won't go into the details, but I'll just show you some plots from the paper that basically this is just to say that it works, at least in certain cases. They can actually measure this. Here they didn't do an experiment on a quantum computer, just simulation, but they can actually go from this modulus of the signal, recover its phase information, from which you can then do the Fourier transform to learn about the spectrum. Okay. So again, this was very interesting and certainly caught my attention. And so the work that we're doing is building off this. Instead of these textbook algorithms, I'm going to propose that we use a neural network to do this phase retrieval. So this is the neural part in the neural quantum phase estimation algorithm. Why would we do this? I have 5 reasons for you. So again, we're retaining the lower resource requirements for quantum computers, no controlled time evolution. if you can reduce the phase estimation algorithm to just doing time evolution, that's something we can experimentally do. It's hard to think about reducing it to less than that. And so in some ways, this is kind of like the lowest resource requirements you can hope to get for a quantum computer. So, I'm thinking of it as optimal for the quantum computer. Why else would we hope to do this? Well, it's a problem that has actually been studied a lot. So there's, for example, a 2024 Nature Review article all about the use of deep learning for phase, in this case, recovery, meaning the same problem as phase retrieval. Okay, so this pops up in a lot of different areas. As far as I know, it has not been applied to this problem in quantum computing for doing phase estimation. But in the same way that it's useful in all these other cases, I expect it to be useful here, and I can show some preliminary results for that. The other reasons that are nice is that this function f of t has some actual physical constraints on it. For example, it has to be skew symmetric. If you take t to be minus t, then you get the complex conjugates. So it has these symmetries and constraints that you can exploit in the design of the neural network to help you learn about this phase. It has what I'm calling a built-in or an embedded error mitigation, which is to say the signal that we get out from the quantum computer is not going to be perfect. It's going to be noisy. But the neural networks are very flexible, and under certain assumptions, we can typical noise models, we can show that you can actually recover the signal in phase from the noisy signal. And so it has this very nice feature. And then also you can, you have a lot of flexibility, of course, in the neural network, depending on the problem, the Hamiltonian that you care about. You can tailor the neural network to, your needs, whatever symmetries that are or properties that the problem has. So in the last few minutes, I'll show you a proof of principle for demonstrating that this works, and then I'll discuss the ongoing work that we're doing to sort of build out this algorithm and do the first non-trivial experimental demonstration of phase estimation. That's really what we're working towards here. So let me go through this quickly. The proof of principle example. I want to consider a common model that people study, the transverse field Ising model, which is defined as sum of ZZ terms with the sum of X terms. And what I'm going to do is I'm going to consider this family of Hamiltonians to be parameterized by this coupling strength J that appears. This is going to provide the training data so that I can train my neural network. And the way I'm going to do this is I'm going to sample a bunch of coupling strengths J, and I'm going to index that by I. I'm going to generate this training data where think about it, the input is the modulus of the signal, and the output that I want is the actual signal itself. The way I'm going to generate this training data for now is by classically simulating the circuit. Obviously not a scalable approach, but we have ideas for how to do this in a scalable way so that you don't actually have to classically simulate the circuit. So general strategy of this I can mention. So two neural network architectures that we've tried. This is like machine learning 101. Like it's very basic stuff here, nothing particularly interesting, but just simple out of the box like feed-forward neural networks have been successful for this problem. So just to highlight quickly, the first one will enforce some physical constraints that we have on the signal. For example, f of 0 is equal to 1. It's skew symmetric. It can be written in this form. So we sample the signal at capital T points. We have a hidden dimension of 256 and 3 layers. And then what we'll do is we'll impose a cutoff for the number of frequency components that we want. That's the number capital K here. And we just pick K to be 32 for these numerics. There are 2K of these because you can think, we want the real and the complex value, real and imaginary parts of the signal. And in this case, we apply softmax to obtain the weights WK. And then we can also get out the energy estimates. So the final output would be the complex valued signal. So that's one way of doing it. That would be like the physics-informed neural network. And we've also just applied very simply a simple feed-forward neural network In both these cases, the activation function is a G loop. This one had 4 hidden layers, similar architecture as above. In this case, the 2 is coming from the real and imaginary parts. So that's why you have that here. Okay. So here's some example of what the signals actually look like. The signal is defined again in this way. We choose some initial state psi. We parameterize e to the minus I h by some time t. And we can look at what these signals look like. So the inputs to our neural network is going to be the modulus of the signal. And then the outputs in our training set that we want will be the actual signal itself. And you can see the variety of signals that you might obtain, at least here for this example of the transverse field Ising model. It works. so these plots are never interesting to look at in presentations, but they're nice when you see the training actually work when you're doing the experiment. So I included that. So we can train and we can actually learn a model for mapping this real valued signal to its complex counterparts. And when we do that, we can then reconstruct signals that we haven't seen before. So here's the example for that. And you can see it's not perfect. You know, there's some points where we're not matching exactly, but generally speaking, we're getting a good reconstruction of the signal. It's sort of ongoing work, related to the amount of accuracy that you want, your desired precision. We need to bound this maximum error that we can get from the neural network, which might be challenging because it's kind of empirical, but we at least can do this and reconstruct the signals to some reasonable degree of accuracy. This is a recipe for generating training data at scale. I can come back to that if there's a question. I just want to emphasize for the last thing, the built-in error mitigation, because I sort of like this feature. Another big component of my research group is, one is developing quantum algorithms and like subroutines for measurement reduction, like I mentioned, but also just to make quantum computers more practical, you need some way of handling noise in the quantum computer in addition to the algorithm that you're developing. So there's a lot of methods which are, for error mitigation, which don't take anything into the problem or the circuit or the hardware into account. And they work generally, but they can be optimized more. So I like the strategy, looking forward of error mitigation as problems or circuits or algorithms which have these sort of built-in or embedded error mitigation properties. And this is one that we have here. So what we can do once we generate the training data in a scalable way, and again, I can mention how to do that if there's a question. But what we can do is we can take it and we can actually simulate it on the noisy quantum computer, and we can obtain a noisy signal f tilde, the magnitude of that, in addition to the noiseless one. So we can sort of augment our training set, not just the modulus of the signal and the signal itself, perfectly obtained, but actually the f tilde signal, the noisy one that we get from hardware as well. And then what you could do, there's several possibilities from this. So you could think about this as a pre-processing step where I want some neural network to go from this noisy signal to the not noisy signal, the perfect one. That's one thing that you could do. So we can think about a pre-processing neural network in order to do this. Another thing that you could do is just try, I think I have this on the next slide, to do this learning directly. Meaning, let's still just use one neural network and let's just try to go from the noisy signal itself to the noiseless signal. And this works actually surprisingly well, at least for the examples that we've tried it so far. This is a model of depolarizing noise, which is the slide that I just skipped, a standard model of noise that people use for quantum computers. And we apply it after every layer of operations in the circuit. So the longer times corresponding to the longer evolution are deeper circuits. There's more noise happening in them. So the signal gets worse and worse. Here in black is the noiseless signal. That's the one here. And then these parameters P are different strengths of the depolarizing channel. So you could think, like IBM or Google or state-of-the-art quantum computer is like 99.99% 2-qubit gate fidelity and maybe one more 9 for single qubit gate fidelity. So this is 1 minus that parameter. So the blue, orange through the purple here. And even though these signals are getting worse and worse over time, we're still able to do this training. So again, the boring plot, but it's exciting that it works. And you can accurately still reconstruct these signals. So here's two examples of that. Signal, modulus of the signal on top, and then the actual signal on the bottom for two different samples. In the sample one, especially, you can see how much the noisy signal is differing from the actual signal, but we're still able to learn its real and imaginary parts. So I'm optimistic about this approach for doing phase estimation. And I'll just leave on this slide as a summary. What we're doing in this setting is we're using a quantum computer to generate the real valued part of the signal. And then we're using a neural network to obtain to do this phase recovery or phase retrieval process from which we can obtain the spectral information. So I think I'm at time, so I'll leave it there and happy to take